We will continue to work with hypothesis testing, but today what we're going to do is we're going to decrease the sample size. Okay? Up till now, we have dealt with hypothesis testing and our sample size has been greater than 30. Okay, just like with confidence intervals, where our sample size is greater than 30, we had our z-value in our t-table that we could utilize to be able to find those critical values. Today, once again, what will happen is we're going to reduce the sample size. And when we reduce the sample size, the only thing that's going to change here in what we've been doing up till now is how we find our critical values. Okay, so finding those critical values is just going to be a little bit different. Okay, so when working with our t-values, once again, our critical values, whatever, what we've stated is a known alternate hypothesis. We sat there, we found critical values here. We found our critical values, and we used z-values that were at the bottom of our t-table for a specific confidence interval, one tail, two tail. These critical values now, we have our non-critical regions. We have our critical region here. Okay, we have our non-critical and our critical region where we reject or fail to reject the null hypothesis. Once again, what will change now is basically this right here, how we find our critical values. We still have a sample size of n. We have a degree of freedom. When we were dealing with our confidence intervals, we dealt with a degree of freedom. We have n minus 1. And what will happen here is to find our critical values now, we will just have to look at our confidence, or I'm sorry, not our confidence interval, our alpha value that we are dealing with, and we have to go to our degree of freedom. So we'll find our critical value somewhere within our t-table. That is basically the only thing that's going to be changing here. Our test value is still going to be the same. It's going to be x bar minus mu divided by standard deviation divided by square root of n. Our test value will be the same. The things that we have dealt with up till now with hypothesis testing is not going to change. The only thing that will change is basically finding our critical values. Take a look at the problem. Study found the average stopping distance of school bus is the same problem, but what I do is I have changed the study to 20 buses. What we did before was we had a study of 40 or 50 buses. I can't remember what sample size we had. We've now changed our sample size to 20 buses. Study found the average stopping distance of a school bus traveling 50 miles an hour is 264 feet. A group of automotive engineers decided to conduct a study on 20 buses now. Average stopping distance was 262.3 feet. Standard deviation of 3 feet. Tested claim the average stopping distance is actually less than the 264 feet. So we're going to still start with our null and alternate hypothesis. Okay, what are they hoping to be true here? That's our alternate hypothesis. Okay, well, what they're testing to claim the average stopping distance of buses is actually less than the 264 feet. So what they hope to do is mu is going to be less than. That's what they hope is true. Your null hypothesis is the opposite of that. Make sure we include equality with the null. So we have greater than or equal to 264. We have a sample size of 20. Stopping distance was 262.3 feet. Standard deviation was 3 feet. we have an alpha value of 0.01. One tail or two tail? One tail, left or right? Left. One tail left, because we look at our alternate hypothesis here. So we have a one tail left, and we have to find a critical value. We have a sample size of 20, a degree of freedom. One less than that, a value of 19. Okay, that's not changing from our confidence interval. But once again, what's changed now is now we need to go down to our degree of freedom of 19 and go over to our alpha value of 0.01. Make sure you go to 0.01, and now we have one tail. We have a one tail. So we have to go to the alpha value of 0.01 on the one tail. Okay, don't go to your two tail, go to your one tail. And we drop that down to our 19. Michael, what do you get?
2.539.
2.539. And since we are doing to the left here, we are going to go negative. Okay, once again, common mistakes are you go to the wrong column, you go to the two tail 0.01, or you go to the 0.10, run the 0.01. Find our test value the same way. X bar minus mu divided by standard deviation, square root of n. So you throw your values in. So what do you get for your test value? Negative 2.53. You take one more decimal place. 253.2534. Yes, no, maybe so. Which puts us right next to our critical value. But we are in a non-critical region. And we have a critical region there. We fall into a non-critical region. So since we fall there, we fail to reject. The null hypothesis of stopping distance being 264 feet. Now, once again, as a person that may be doing this study, we're right next to it. They're going to sit there and go, okay, I don't have enough evidence to reject it right now, but I'm going to do a study again and maybe increase my sample size, and maybe I can get to fail or reject my null hypothesis. Average family size was reported to be 3.18 students, people. Random sample of families in a particular school district result in the sample size of the following sample sizes. Alpha value 0.5. Does the average size differ from the national average? The key word there is differ. So what are we going to be using for our symbols then, Anna?
This is an equals and not equals.
Equal to and not equal to. Once again, we have data values here. So you're going to want to enter in your data values because all we have is we have an alpha value of 0.05. So you're going to have to calculate an X bar, standard deviation, and what is our sample size here? So enter into your into your table. You may need to clear your memory because you might have more values than you want there. Once again, clearing your lists. To clear your list, hit your second value and your plus sign. Option 4 clears your list. Second value, your plus sign, option 4 clears your list. So now you can enter in your data values. Okay, go to your stats, your calculate one variable statistics. You can pull off your X bar 3.83 and your standard deviation 1.43. We have 24. So a degree of freedom of 23. Once again, need to practice just using your calculator. Okay, equal to, not equal to. Got our two-tailed test. So go to your degree of freedom of 23. Degree of freedom of 23. Alpha value 0.05, two-tailed test. What's the way you get for a critical value? 2.069. A negative 2.069. We have our test value, x bar minus mu divided by standard deviation divided by square root of n, which is 24. Make sure you get 24 in there. Jace, what do you get for a test value?
2.278.
2 point what?
278.
278, which throws us non-critical, critical, critical. So we have 2.278. Those is out here in the critical region. So we can reject the null hypothesis. Yeah?
It's 2.227.
2278. Wait, 2.2278. Okay, it still takes us out into a critical region, so we can reject the null hypothesis of national average or family size of 3.18 people. Now, what I want you to also do now, okay, is we can also take a look what your calculator will do for you. Once again, we are dealing now, because we have less than 30, we now have a t-test. So if we go to our stats and our tests, okay, stats and our test. If we go down to our t-test, now, what your calculator will do for you, it will pull the information from your table for you. But you have to go to, rather than just entering in statistics, we now have data. So you have to go over to data and hit enter. Okay, so data is now highlighted, because what that's going to do is that's going to pull us our data from our list 1. Our mu naught is 3.18. Okay, we're pulling from list 1, which is what we want, our data from list 1. Frequency thing you don't have to worry about. Our null and alternate deals with the equal to, our alternate deals with the not equal to. So we can now go down to our draw and hit enter. Once again, we get our bell-shaped curve. As you can see, the bell-shaped curve gets a little bit higher because we have that family of curve. So the t-value puts the curve a little bit higher. Okay, we got our 2.2311. It's pulling statistic data values out of that. And we also got our p-value down there, which we talked about on Friday. Okay, once again, you can utilize that p-value to be able to make verify your hypothesis to the null or alternate. And like I said, that's what we talked about on Friday. Okay, our value is a little bit different because it's pulling data values here, exact values here. But your calculator will do things for you, which is nice. Once again, what I want to see is I want to see you setting this up, and if you use your calculator to determine that is fine, but I want to see you just setting this up, and if you want to utilize your p-value, that is fine. You don't want to use the p-value, this does the exact same thing. I want to see a setup here, and I want to see what these critical values are over here. Okay, how you determine this right here and how you determine this right here You can look at p-value, or you can look at your calculator to be able to determine that for you. KYC, there's your calculator. Does a lot of nice things for you. We can also test variance and standard deviation. Okay, we state the null and alternate hypothesis. It's going to be the same. Identify one tail or two tail. Degree of freedom. Find critical values from the table. Now, how we find our critical values from the table? We have our degree of freedom, which is your n minus 1. If it is a left tail test, you go 1 minus alpha. If you have a right tail test, you use alpha. If you have a two tail test, you have to come up with two values for critical values. You have 1 minus alpha divided by 2, and then alpha divided by 2. Now, what I will allow you to do, okay, on your chi-square table here, on your chi-square table, you can write down left tail, use 1 minus alpha. Right tail, use alpha. And two tail test, use alpha divided by 2 and 1 minus alpha divided by 2. So you can write that down on your chi-square table. You will not be asked to remember that. Okay, you can use that. That's fine. And you use these values and your degree of freedom to be able to calculate your critical values. Okay, you calculate your test value. And if you want to write that down, that is fine. Your chi-square test. This is your test value. Take your degree of freedom, S squared divided by sigma squared. That's your variances. Degree of freedom, sample variance divided by population variance. If you want to write that down on your chi-square table, that is fine. Even if you want on the other side, if you want to write that down the other side, that's fine too. If we use enough, you should be able to, it goes back to our central limit theorem idea, but if you want to write it down, that is fine. Weather Service claims standard deviation. Number of fatalities per year for tornadoes is more than 25. I don't really, why they worry about the standard deviation, not quite sure. One death is one too many. You should be talking about the average number of deaths. But that's just my own personal opinion. Random sample of number of deaths for 28 years has a standard deviation of 31 fatalities. Alpha value 0.10. Is there enough evidence to reject the claim? Okay, we can take a look at the idea that there were more than 25. But now the difference to this is we are now looking at the standard deviation. We are not looking at the mean. We're looking at the standard deviation. So now we're looking at sigma and sigma. We're not dealing with the mean and mu anymore. We're dealing with sigma. And what they hope is true, and once again, it's not a good thing, but what they hope is true is it's more than 25. So that's our ultimate hypothesis, because that's what they're hoping is true. So we are less than or equal to the 25 here. So if we take a look, yeah, let's see, for 28 years, n is 28. The sample standard deviation is 31. We have an alpha value of 0.10. Degree of freedom is 27. So I know your chi-squared curve is not the same as a bell-shaped curve. But for me, because if you look at the bottom of your chi-squared table, it looks like a bell-shaped curve that's skewed a little bit. To me, I just need a visual. I need a picture. So even though it's skewed, I'm still going to make it look the same. Because I just, once again, it's for my own brain to get a visual down there. One tail, two tail, left or right? If it's one tail. What do we have here? One tail, no, what do we have here? Left tail, right tail, one or two?
It would be right tail.
Right, one tail, right? So we're over here. Once again, we can look at the ultimate hypothesis. So if we have a right tail test, okay, we have a right tail test, we just use alpha and the degree of freedom for our critical value. So we're just going to use the 0.10 and our degree of freedom of 27. So in our chi-squared table, we have 0.10 and we go down to 27. Alex, what do you have?
1.314.
No, 0.10 alpha value on the table here.
Yeah.
Go to your alpha equal chi-squared on the chi-squared side, not t distribution.
Not
There
bad.
you go. 0.10 all the way down to 27.
35.5663.
That's 26.
36.7.
There we go. There's a winner chicken dinner. 36.741. So now we look at our chi-squared test. It's our degree of freedom, n minus 1, our sample variance divided by our population variance. These are just S's and sigmas, so we have to square these values. So we have our S squared, which is 31 squared, divided by 25 squared. That's our sigma value. Adam, what do you come up with?
41.52.
41.52. Just now, maybe so. Okay, once again, we have non-critical. We have critical. It still stays the same. Throws us out here. It's just a number line into our critical region, so we can reject the null hypothesis of standard deviation equal to 25. And it's actually greater than 25. Doctor says standard deviation of length of stays for parties involved in crash, patients involved in the crash, the vehicle struck a tree is 6.14 days. Random sample 20, the length of stay, that standard deviation is 6.5. Out by 0.05, reject the doctor's claim or not. Doctors claim that the standard deviation is 6.14. Okay, that's what his claim is. So that's what he is hoping is true, or that's what he's hoping is true. Once again, equality will always go with the null hypothesis, even though this is what he's hoping that is true. That's that one time, this is that one time where that what he hopes is true goes into the null hypothesis. As I talked about before, that sometimes that occurs. But the null hypothesis is the only thing that we can reject or fail to reject. We have a sample of 20. Let's see, standard deviation for that sample 20, 6.5 days, alpha value 0.05, degree of freedom is 19. Okay, we are in two-tail. We are at two-tail. So if we are two-tail, we use alpha divided by 2 and 1 minus alpha divided by 2 for our critical values. So alpha divided by 2 is 0.05 divided by 2, 0.025. And then 1 minus that, 0.975. So we look up those two values in our chi-square table. We have alpha divided by 2, so we have 0.5 divided by 2, 0.025, and then 1 minus that is 0.975. So go ahead and look them up, find your critical values. Find your test value. We do 8.907 and 32.832. With your test or your critical values. What do we get for a test value? Mike, what do we get? Anybody get test value? Grayson? 21.229, which throws us into here, which is 9 critical. Okay, so we can fail to reject a null hypothesis and accept the doctor's claim. We can accept it and have the standard deviation of 6.14. Now, I combined 2 days worth of lessons into 1 day here because it's really nothing too different. Okay, my suggestion just do a couple from each, maybe just do the odds or take 2 or 3 of them from each and do from your homework. Both sets of homework solutions are on Classroom, so just do some of each. All right, adios, have a good day.